We open it up for questions, starting here at headquarters, moving on to our centers, and we have a number of media on our phones. We'll have brief presentations. Our presenters will have visuals. For those out there by their computers, go to www.nasa.gov/Hubble, where the images will be posted. To facilitate the presentations, it's my pleasure to turn it over to a gentleman who, quite frankly, ladies and gentlemen, when you mention Hubble Space Telescope and his name, it goes hand in hand. And he's been with the Hubble since the very beginning, either directly or indirectly. I'll turn it over now to the head of NASA's Science Mission Directorate, Dr. Ed Weiler. Ed?
Thanks, Dwayne, and good afternoon. Let me just set the context a bit here. About 18 and a half years ago, it was a couple days before the launch of the Hubble Space Telescope, April of 1990. And many of us Hubble scientists were privileged to be able to speak to the press about Hubble and the science that we wanted to do. And the most common question, of course, was what were the greatest goals of Hubble? And I remember very specifically the presentation I gave at the Kennedy Space Center that April day in 1990. And it included things like we would go out and try to determine the age of the universe, determine the Hubble constant. We would try to figure out whether black holes were fantasy or whether they were real, and on and on and on. And the very last chart in my view graphs that day, we used view graphs in those days, was a chart that I knew and most of the scientists knew was a real wild, crazy idea, probably never happened. But we said if things were just right, if we found a star that was just the right brightness and just the right distance, that maybe, just possibly, with the right technological advances over the years, we would get that first picture of a star, a planet around another star. You got to understand the context of what that meant in those days. In 1990, nobody had detected any planets around any star. We astronomers knew there had to be other planets around other stars. After all, there are 100 billion trillion stars in the universe. That's 10 to the 23rd for you scientists out there. There had to be other planets, but we had not seen or detected one. In the subsequent 18 and a half years, we have ground-based astronomers have found hundreds of stars, of planets around stars, but only by indirect methods, by the effect the planet has had on the star, either tugging it gravitationally and moving it or changing its velocity. The analogy I like to think of is if I live near a jungle and I hear elephants at night and I go into the jungle in the daytime, I see what look like elephant footprints. I might think I've detected elephants, but until I get that picture, that simple picture of an elephant, I'm not really sure. So to me, this is a 18-and-a-half-year dream come true. We were going to show you, the scientists here today are going to show you the first visible light image, light that you can see with your own eye, of a planet. Not just one, but two images. So I'm going to introduce the panel now, and then we'll start. To my immediate right is Paul Callis, who's an assistant adjunctive professor from the astronomy department of the University of California at Berkeley. To my right next to me is Dr. Mark Clampin. He's the James Webb Space Telescope Observatory project scientist, and he's at the Goddard Space Flight Center in Greenbelt. To my immediate left is Dr. Sarah Seeger, who's an associate professor of planetary science at the Massachusetts Institute of Technology in Massachusetts. And to my far left is Dr. Mark Kushner, who's an exoplanet scientist at the Astrophysics Science Division at, again, the Goddard Space Flight Center. So, Paul, tell us what you found.
Oh, thank you very much, Ed. I'm delighted to be here. And the reason we're all here today is to show you the first visible light pictures of a planet orbiting another star. The star in question is called Fomalhaut. It should come up on your screen shortly. Fomalhaut is one of the 20 brightest stars in the sky, easily visible with the naked eye. And that makes planet detection very difficult because the glare from a bright star blinds us to the faint signal from a planet that may be in close proximity to the star. So what we did in 2004, we used a new instrument aboard Hubble called the Advanced Camera for Surveys, which has a special device called a coronagraph. A coronagraph essentially produces an artificial eclipse of bright stars, thereby removing the glare from the star so we could be sensitive to the faint light from planets. The big surprise in 2004 was that we didn't see the planet immediately. We saw this vast dust belt circling the star. This is an analog to our Kuiper belt, a system of icy bodies that are colliding and continually producing dust that we can see in reflected light. And back then what we saw is that the belt has several unusual features which we hypothesized could be due to the gravitational perturbations from a planet that had not been seen yet. So with this hypothesis in mind, we returned to Fomalhaut in 2006 with the advanced camera for surveys, obtained even deeper and more accurate images of the belt, but also found a faint point source to the lower right. Now we'll see a white box, show up to the lower right, and that faint speck is Fomalhaut B. Here it is in 2004, and here it is in 2006. Fomalhaut B is moving because it's orbiting the star Fomalhaut just within the dust belt, thereby satisfying our hypothesis that the belt is governed by this planet. You can see the orbital motion is actually counterclockwise, and Fomalhaut B completes an orbit in roughly 800 years. How do we know Fomalhaut B is a planet? Well, we use two different techniques, and we come out with the same answer. First, we measure the brightness of Fomalhaut B. Turns out Fomalhaut B is one of the faintest objects outside of our own solar system. It's 1 billion times fainter than the central star. If Fomalhaut B were a brown dwarf or a star, we would have seen it to be much brighter and easily detectable. We are confident from the faintness of Fomalhaut B that it's less than 3 Jupiter masses. The other technique we used is illustrated in this animation, which shows the gravitational effects of a planet on a dust belt. The thing to keep in mind is that the dust belt is being sculpted by the gravity of the planet. And by measuring how close the planet is to the dust belt, we can estimate the mass of the planet. Because, in fact, if Fomalhaut B were very massive, the gravity from a massive planet would completely disrupt the dust belt. For the dust belt to be preserved in its current state, Fomalhaut B has to be less than 3 Jupiter masses. In fact, our lower limit to Fomalhaut B is Neptune. To tell you more about Fomalhaut B, I'll turn it over to my colleague, Mark Clampin.
Thank you, Paul. If we can have the first image, please. One of the key aspects of this discovery is that the dust belt is associated with the planet. So we're actually seeing the starting of a real planetary system architecture here. And it's actually very interesting that one of the interesting aspects is that the planet was discovered by direct imaging, but it had been previously predicted both by our own Eugene Chang, theoretical modeler, and by other independent researchers, just on the basis of the properties of the dust disk. And as Paul said, the properties of the dust disk, combined with the image of the planet, actually allow us to firmly constrain the mass independently of its brightness. This is a very important part of this result. In order to put this system in context, what I'd like to do is to show you the next image, which just shows a comparison between our system, our solar system, and the Fomalhaut solar system. And if we can put the comparison slide up, that would be great. And it just gives you some idea of the differences in scale. So there are some similarities between the two systems, and there are also a lot of differences. Fomalhaut is a brighter star than our sun. It's 16 times more luminous. And you can see that the whole system is on a much grander scale than our own solar system. But there are some similarities as well. Fomalhaut B is orbiting around the inside of this dust belt and dynamically sculpting and shaping it. And the similar thing happens in our own solar system. And you can see in the figure below, and if you go to the next slide, there's an enlargement of our solar system. Neptune in our own solar system does a similar thing, basically sculpting the inside edge of the Kuiper belt, a dust belt, around the outside of our own solar system that's very similar or analogous to the one you see around Fomalhaut. So there are some similarities, but there are also significant differences. And we're going to be finding out about those over the next few years as we study this object in more detail.